Welcome to an example on how to apply Stoke's theorem to evaluate a surface integral. We're given the vector field f, and we're asked to use Stoke's theorem to evaluate the double integral over the surface S of the curl of f dot differential S, which is often also expressed in this form here, which is equivalent. We want to evaluate this where the surface S is the part of the paraboloid z equals 11 minus x squared minus y squared that lies above the plane z equals 10, oriented upwards. Let's first review Stoke's theorem. Stoke's theorem states that if S is an oriented surface with unit normal vector n, with a piecewise smooth closed boundary C, with a positive orientation, and vector field f with components p, q, r, all have continuous partial derivatives, then the double integral over the surface S of the curl of f dot n differential S is equal to the line integral along the closed curve C of f dot differential r. So this surface integral is equal to this line integral under these conditions. So this states the relationship between line integrals and surface integrals of a vector field. It tells us the net rotation over the surface S is equal to the net rotation on the boundary C given the above conditions. So going back to our example, let's look at what's happening graphically. The graph of the vector field f is in gray, the paraboloid is graphed in light green, and the plane z equals 10 is graphed in yellow. So we're trying to evaluate the surface integral over this light green surface that's above the plane z equals 10, and by applying Stoke's theorem, we can evaluate this double integral over the surface S by evaluating the line integral along the boundary curve C, which would be this circle here. If we look down on the xy plane, notice how we can see the curve C is going to be where this yellow plane cuts the paraboloid, giving us this circle here, centered at the origin, with a radius of 1 along the plane z equals 10. Going back to our problem, again by applying Stoke's theorem, the double integral over the surface S of the curl of f dot differential S under these conditions can be evaluated by using the line integral along the curve C of f dot differential r. Looking at our notes below, to evaluate this line integral, we need to first parameterize the curve C using the vector function r of t. Then the line integral along the curve C of f dot differential r equals the integral from a to b of the vector field f expressed as a function of t dotted with r prime of t dt. So let's begin by parameterizing the curve C using the vector function r of t. Notice how if we substitute 10 for z into the equation for the paraboloid, we would have 10 equals 11 minus x squared minus y squared. So if we move the variable terms to the left and then subtract 10 on both sides, we'd have x squared plus y squared equals 1, which gives us the curve C, which remember is in the plane z equals 10. So I've also shown the curve C here in blue. Keeping in mind though, this is a z equals 10 trace. So when it comes to parameterizing the curve C, remember if the circle was in the xy plane, using parametric equations, if the circle is centered at the origin with radius r, we can always let x or x of t be equal to r cosine t, and y or y of t be equal to r sine t. So for the vector function r of t that traces out the curve C, we can let the s component be equal to cosine t, the y component be equal to sine t, and then for the z component, because this is the z equals 10 trace, the z component would be 10. We're also going to need r prime of t, so let's find that now. The components of r prime of t would be the derivative of the components of r of t. So the derivative of cosine is negative sine t, derivative of sine t is cosine t, and the derivative of 10 is 0. And then we also need to write the vector field f in terms of t. So f of t would be equal to, well, using the parameterization of the curve C given by r of t, notice how x equals cosine t, y equals sine t, and z equals 10. So the x component, which is negative yz, would be negative sine t times 10, or negative 10 sine t. The y component is x times z, which would be cosine t times 10, or 10 cosine t. And the z component is x times y, which would be cosine t sine t. So again, the given surface integral is equal to the line integral along the closed curve C of f dot differential r, which is equal to this integral here. So this equals the integral from a to b, we'll figure out a and b in just a moment, of f of t, which we found here, dotted with r prime of t, which we have here, dt. And now the values of t will trace out this unit circle counterclockwise on the plane z equals 10 would be when t is from 0 to 2 pi all the way around the circle. Let's go and evaluate this on the next slide. So now we'll find the dot product. So we have negative 10 sine t times negative sine t, that's 10 sine squared t. Then we have 10 cosine t times cosine t, that's plus 10 cosine squared t. And then we have cosine t sine t times 0, which is 0, so we just have dt. Notice here, if we factor out 10, we have 10 times the quantity sine squared t plus cosine squared t, which simplifies to 10 times 1. So we can write this as 10 times the integral from 0 to 2 pi dt if we want 1 dt. So the antiderivative with respect to t would just be t. So we just have 10 and then t. So evaluating here, we have 10 times the quantity 2 pi minus 0, which is 20 pi, which is the exact value of the line integral as well as the surface integral. As a decimal approximation, this is approximately 62.8319. So going back to our graph just for a moment, this value represents the net rotation along the surface S, which is the part of the paraboloid above this yellow plane, which is equal to the net rotation along the curve C, which is where the yellow plane intersects the paraboloid, this circle here. I hope you found this helpful.